네, 그러면 웨비나 시작하도록 하겠습니다. 네. 안녕하십니까? 주한이스라엘대사관 경제무역대표부 송지훈 상무관입니다. 바쁘신데도 불구하고 이스라엘 인공지능 기술 세미나에 참여해 주신 여러분께 감사 인사를 먼저 드립니다. 시작하기에 앞서 간단히 금일 행사 안내를 먼저 드리고자 합니다. 우선 발표 순서는 화면에 보시는 것처럼 Classiq, Run AI, Cybord 순서로 진행이 됩니다. 사전에 안내드린 것처럼 참여 키로 하였던 대시 AI는 사정상 금일 참여를 못하게 되었습니다. 혹시 대시 AI와 연락을 원하시면 저한테 별도로 연락을 주시기 바랍니다. 질문이 있으시면은 발표 중에 질문을 하실 수 있습니다. 화면 하단에 Q&A 버튼을 통하여 질문을 하시면 되고요. 한글로 남겨주셔도 무방합니다. 그리고 세미나 후에 발표 업체와 별도 미팅을 희망하시면 저한테 연락을 주시기 바랍니다. 또한 업체별 연락처 메일을 추후 공유드릴 예정이오니 직접 연락을 하셔도 무방하며 이 경우에 저를 꼭 첨부로 넣어주시기 바랍니다. 그러면 먼저 저희 경제무역대표부 대표이신 타마르 코시아 대표님의 인사말로 시작을 하겠습니다. 타마르, please make a greeting for you.
Hello, everyone. 안녕하세요 and shalom. Nice to see you all with us here. I am very happy to host this webinar and to have three amazing AI companies from Israel in very different sectors with different solutions. Thank you all for joining us, and please feel free to ask many questions and to ask Tune and me for anything we can do in our office ITO to support your business with Israel. Thank you. 감사합니다.
Thank you, Tamara. 네, 다음으로는 Run AI의 죄송합니다. 다음으로는 첫 번째 발표로 클래식Q의 퀀텀 어플리케이션 엔지니어이신 닥터 샤하프 아스반님의 발표가 있겠습니다. Dr. Asban, the floor is yours.
Thank you. Thank you very much for this opportunity to share a little bit of what we do and the solutions with regards to quantum AI. So let me first start by sharing my screen. Okay.
Okay.
Can you see my screen?
Yes.
Perfect. Okay. Okay. So this is me, Shahaf Asban, PhD in physics. Today I'm going to present some of the implications or our approach to solutions in artificial intelligence using quantum computers. So first I'm going to start with our agenda here. I'm going to give you a little bit of a motivation why are we interested in quantum computing in the first place, and then how are those machines are programmed? How do we program them today, and what are our vision to program them tomorrow? And then I'm going to go over to the more specifically to quantum machine learning using Classiq platform, and briefly show you something that we have implemented there, which is QGUN's quantum generative adversarial networks. So this is essentially our agenda for today. So let's start with the motivation. So one of the first motivations for quantum computing is, I think it was in the 70s, 80s, where Feynman already envisioned those machines, was quantum simulation. And quantum simulation actually have a lot of implications and enhancements of what we do today. For example, in drug design, tailored chemical reaction for designing better and more accurate and high yield medicine. For material design, we requested properties that are hard to design with classical computers, that just blow up at a certain stage. Quantum computers can do it linearly. Another thing is emission reduction, especially for recycling processes. And just to name the last one, which is not really the last one, the last one I'm going to show is battery design, more efficient energy management, energy flow, and energy banks. So this just to name a few from the quantum simulation side. Another implication is optimization. Those machines are actually natural optimizers, using very simple quantum models on quantum computers that can be actually connected to the simulators that you saw above. We can also apply them to optimization processes in derivative pricing in finance, for example, or in logistics for supply chain problems, or in even behavioral sciences in modeling of trend propagation, for example, as voter modeling, or for advertising, everything that's got to do with propagation of trends within the community. So these are the main things that I chose to show you, but now let's go deeper into the quantum machine learning. In quantum machine learning, well, the quantum computers are postulated or let's say promised to revolutionize the fields with respect to several applications. Feel free to click those links afterwards. I'm going to leave the slides here. In chemistry, finance, medicine, image recognition, even demand forecast, essentially time series analysis, and even cryptography. So these are just taste of what quantum computing can do in machine learning or AI specifically. So let's start with what are quantum computers real, just a taste of that. So those essentially new types of calculation machines. They actually work given two fundamental mechanisms from quantum mechanics that are superposition and entanglement. Superposition is essentially some mechanism, internal mechanism of quantum mechanics that allows natural parallelization. So several processes can happen simultaneously, and that can be used in algorithms that have huge search space, for example, or as follows. The entanglement part is, in some cases, when they're meticulously engineered, quantum correlations can exhibit stronger correlation than classical allowed mathematically. So this also yields very interesting phenomenon with respect to cryptography, communication, you name it. So these actually help us in, well, showing computational speedups theoretically and unique functionality mathematically of what they are capable to calculate. How is it relevant for AI? So the main things that I'm going to show, at least today, or in our notebooks, are unique kind of kernels used in certain machine learning algorithms and in optimization algorithms as well. Okay, so now we can jump deeper. Oh, okay. So feel free also to scan this QR afterwards. That actually leads you to Classiq's page of quantum machine learning. So now we're going to the second part, which is how do we actually program those machines? As you saw in this picture, this seems like very complicated machine. It's very different from the classical one. How do we actually program them? And the answer is that today, those machines are programmed via circuits. So let's see how this looks like. Quantum programs or quantum circuits are essentially, as you can see here, for example, is a manifestation of some kind of a network that flows through time. So let's imagine that these 4 entries are quantum bits. They're the analog of classical bits in a computer. They're initialized to some state. For example, they're initialized to 0. And then they evolve through time. And what you see here is essentially the sequential time evolution of the information flow. And each one of these rectangular objects here or circular objects here are manipulation on the qubits in time that actually shapes, or well, this is the calculation to be exact. This is the exact calculation process that's being done. Eventually, they are measured, and from the measurement, we infer the result. So this is how it's done today. And for our interest, a special kind of quantum algorithms or quantum circuits are the variational quantum circuits. And in a minute, you're going to see how similar it is to what we know from neural networks. So variational quantum circuits are circuits that have several parameters. Those parameters can be changed externally, classically. So if we would like to train them to do something specific, we would follow something very similar to how we train a classical neural network. For example, this is taken from the paper that you see here. What happens here is that we have a certain circuit with certain gates, a certain architecture. And at the end of the evolution, this circuit is measured. And we compute classically some kind of scalar function, which is corresponding to a loss function, okay, some kind of criteria. And this criterion is minimized, or can be even maximized, but essentially minimized such that at the minimal value of this function, the obtained results give the best solution to the problem that the circuit is designed to solve. So this is very similar to classical neural network, and then you can see that the relation between them. So what we're going to focus here today is hybrid neural networks. And what I want you to get out of that is how easy it is to implement it on our platform. So a hybrid neural network is, in general, a network that contains several classical layers like convolutional layers, activations, exactly like you would do in a classical neural network, and also some quantum circuit as a layer, as a specific layer inside this deep network. Okay, so what are the challenges in doing something like that? The challenges are specifically from the way that we've programmed them today. Today, it's impossible to reach the level of complexity that one would like to in classical neural networks using quantum way of design, approach of design such circuits. And the problem is that you can only go so far designing them by hand as people do today before you see the complexity becomes larger and larger. So the question is, how do we solve this? And this is exactly what Classiq does. Classiq actually provides from given user-defined high-level functional model, functional algorithm design, our synthesis engine actually essentially compiles and optimizes gate-level circuits. So the user doesn't have to deal with the circuit themselves. And afterwards, it goes to execution, where execution can be done on any of the world-renowned vendors such as Bracket, Azure, IBM, or any other Rigetti, any other gate-based computing platform that can be sent directly to them. So how does this work? So I'm going to show you a short example of how do we design a quantum generative model, quantum generative adversarial network, and hybrid one, which is as complicated as you can imagine. And I'm going to show how easy it is to do it with us. So first of all, feel free to jump into our demonstrations and Python SDK based notebooks on QSVM, which is quantum support vector machines, or the QGuns that I'm going to show today, or quantum autoencoders as well. So all of this is available in our user guide. So let's start with the QGun architecture. What we're going to show you today is the design of a hybrid generator. The generator is neural networks that, given some input, for example, noise, can generate synthetic data or fake data, and a discriminator. Discriminator receives the synthetic data and also real data from our problem of choice. And both of them are trained together via the joint loss function, such that the generator's goal is essentially to manage to fool the discriminator, and the discriminator's job is to not be fooled easily. So this process converges when they're tied, essentially. So let's see how something like that might look like using our platform, our Python SDK. So this is, for example, an NN model taken from PyTorch. This is a very standard block for designing the architecture of very simple discriminator. And now let's go to the quantum or hybrid quantum generator. Here you can see, for example, the classical parts that you would do in your everyday programming anyway, but you insert another layer called Q layer. This Q layer is the quantum layer that you design via the circuits. You can take those circuits either from us, we have several of them prepared, or you can also get them directly from papers that have shown how they have implemented them and actually characterized their running results. So this how seamless and easy is to integrate quantum layers inside your existing quantum machine learning neural networks, specifically QGuns. So apparently I finished quite fast. So any question about this design will be welcome right now. And also make sure to check out our platform or contact me with any details that you're interested in.
Thank you, Dr. Arslan. But then you have some time. So what about explaining some kind of a business model cooperate together with the Korean companies?
What about what? Can you repeat,
the
please?
business model of a collaboration.
Okay. So I'm more of a tech guy, but I'm going to try my best to give you an honest answer.
Just briefly.
I can jump in if you want.
Sure. Just a small remark about the business model. Right now, we sell licenses. Those licenses gives you the ability to commercially use Classiq platform. And they also include some level or some degree of workshops and teaching from our end how to use and how to write in Python in the QMod language, which is specifically for the quantum circuits. And also there's some kind of partnership plan, but for that you're going to have to ask our business associates and not me.
Right. So, June, if you don't, I'll jump in and add to Shachav's response. So usually when we engage with new customers, we try to understand, what's their interest, what are the use cases that they're interested, in AI or in, as Shachav demonstrated, chemistry or optimization. There are many different use cases relevant for financial companies. And so anyway, we identify the use case, and then we usually start the engagement with a proof of concept project. It usually takes a few months where as most companies are new to this area of quantum computing. So we do spend time training them and working with them on showing with them how to use our platform, how to instantiate, create, develop quantum algorithms. And we have experience working with people that had zero knowledge of quantum computing. They were AI experts actually, and within a few weeks they were developing QNN models and running independently. And of course, if this is successful, if the customer is satisfied, then we go into a license agreement.
Okay, thank you, Avi and Dr. Aslan. Yeah. 추가적인 질문이 있으시면은 아래 그 Q&A 버튼을 통해서 남겨주시면은 또 답변을 드릴 수 있도록 그렇게 하겠습니다. 네, 그러면은 지금 클래식 키오 발표를 마쳤고요. 네, 다음으로는 그 런 AI의 시니어 디렉터이신 닐 루블라이너님의 발표가 있겠습니다. So, Mr. Lubliner, the floor is yours. You are on mute. Yeah.
Oh, yeah, thank you. I'm just sharing my screen. Just let me know once it's visible. See my screen?
Okay. Yes.
Cool. So nice meeting you all, and Jihun, thank you for giving us this opportunity to present Run AI. I will share briefly what Run AI is doing and what is the problem that we are solving. So a little bit about Run AI. Run AI, as you've mentioned, is an Israeli company, and we work across the globe, worldwide, with various types of customers. As you can see, the customers are not related or are not linked to a specific vertical. We are working with big banks like DBS or Credit Agricole. We work with gaming companies like Sony. We work with health organizations like Kaiser Permanente. Essentially, I would say that we are agnostic to the company. Any company who is involved in doing AI research, we can bring value, and it doesn't matter which vertical this company belongs to. So to start a little bit about the issues that we found out, and I would say why Run AI was born or was established. So I assume, and I hope so, that everybody knows and understands that today the de facto standard of orchestration in the AI is Kubernetes. It is mostly the de facto standard. Everybody is using Kubernetes, various types of Kubernetes. It can be the CNCF vanilla, or it can be any managed service like OpenShift or Rancher or cloud like EKS or GKE. But today, when you are running AI ML workloads in cloud native environments, containerized workloads, microservices, all the ecosystem is tuned towards Kubernetes. But Kubernetes is a great tool for orchestration. Google did a great job. But when they thought about Kubernetes, they were less thinking about how to manage the resources when it comes to AI. And Kubernetes today has some fundamental things that creates very, very problematic things and very low utilization to the users. I will mention only a few which are critical to my understanding. First, today in Kubernetes, the allocation and provisioning of GPUs is not something which is dynamic. GPUs are provisioned under a namespace in Kubernetes. And if this user is very nice and he disconnects from the GPU after he finishes his job, then the GPU comes back to the pool. If he is less nice and hugging the GPU, because today it's very hard to get GPUs, then this GPU can sit under a team or a project or a person's namespace for hours or days, not being utilized. Add to that when you approach a GPU cluster, typically in the AI, we are talking about interactive training and deployments and inference, right? And users can do several types of jobs on the cluster. And each job can come with different tool sets, right? If you are using your Jupyter to build your model, it's nice. If you are training, you can train, I don't know, with Kubeflow. If you deploy, you can deploy with Triton. Each tool or each job will require different amount of resources, but still, all the users are approaching the same cluster, and they require different amount of resources, different use cases. And today, the admin or a specific company does not have any ability to tune the cluster, to set policies, priorities, to define exactly how your cluster will look like, right? So if we are summarizing everything, and there are many, many more things, if we are summarizing this, what we see across the board and is very low utilization. As we all know, GPUs are very expensive, and it's a pity that in most companies, the utilization is very low. In most cases, the admins or the guys who are managing the cluster are even not aware that the utilization is very low. they sometimes confuse between utilization and allocation. They think that, wow, all my GPUs are allocated, but they don't even know that they are underutilized. And on the one hand, they invest on a very expensive infrastructure and hardware. On the other hand, their users are starving for GPUs, and they don't understand what's going on. Like why they do not get to their goals? Why don't they achieve their targets? And this is what Run AI came to solve. Okay, so Run AI has developed a software. Our software sits on top of the Kubernetes layer. I will later show and explain a little bit about the stack. We sit on top of the Kubernetes layer, and we bring very, very smart resource management solution to your cluster. And it goes both for GPUs or also CPUs. The goal of Run AI is that all the GPUs will work 100% of the time to the users, right? So, and I will discuss it, we have many ways of doing it, but the end game, the focus or the target of Run AI is to bring you to maximum utilization, right? We want the GPUs that you have bought to work 100% of the time, no idle GPUs. Every person, every user, every group, every division will have on-demand access to GPUs, right? And we should not forget the admin, which should have really easy way to manage the cluster, to have a line of sight into what's going on into the cluster, to have the ability to influence how he wants to treat the cluster. So this is, in a sense, what the software is doing. And I will show you what happened now when people are using our software. So a little bit about the stack, where we are. So below, we have the infrastructure, right? We have the GPUs, the CPUs, RAM, data, memory. Today, Run AI supports all NVIDIA GPUs, right? We support all the type of NVIDIA GPUs. We are soon going to have support also for ARM GPUs. And we need Kubernetes, any type of Kubernetes, like I've mentioned. So for us, the prerequisites are mainly NVIDIA, soon ARM, and Kubernetes. If a customer is using these two or have these two, for us, we are good to go. We do not care where the cluster is located, whether it's on-prem, cloud, hybrid. We do not care about the use cases, right? As you have seen before, we do not look into the containers. So it doesn't matter to me if a user is working for Kakao, if the user is working for Naver, if the user is working for SKT or any other company. For us, we do not look into the data. We are not interested in the data. We simply make sure that the users, whatever cloud native tools that they will be using, will get on-demand access to GPUs. And for that, we have several ways to do that, which I will discuss briefly because there are many layers into the Run AI platform. But essentially, the important thing is that when you onboard Run AI, users do not need to change any tools. They do not need to change their code. They can continue using the same tools that they are using, but the access that they will get to resources, their day-to-day job will be changed dramatically. So the first part that we have is a very smart scheduler, right? We create a pool out of all your GPU cluster, out of all your GPUs, and it doesn't matter if you are having a homogeneous or heterogeneous GPU clusters. We know how to handle all types of GPUs. And we give the admin the ability to set different policies and priorities first to the cluster. Not every company has the same use case, same number of researchers, same number of projects, same number of teams, different types of GPUs. We want to have this ability of the admins to set different policies and priorities. Which user will get access to which GPU? If two users are asking to get resources, who will be prioritized? It's not one product fits all. So one customer who is using Run AI is not using it in the same way that other customers are using it. So again, the admin can set different policies, different priorities that will be tailor-made to this company. Another fundamental thing that we have is what we call guaranteed and over quota. And again, this is a game-changing thing because today, due to the fact that users are, I would say, hugging their GPUs because it's very hard to get them, we have a mechanism called guaranteed quota. It means that if the admin has decided that users has, or a specific user has a guaranteed quota of 2 GPUs, our system will always grant this user 2 GPUs. The admin can even decide whether it's a specific GPU or it can be a random GPU, but the quota will be always guaranteed. On the other side, what we have is an overquota, and this is also something which is unique to Run AI. It's a mechanism that knows how to detect idle GPUs and simply push them to the users, right? So if, for example, I am in a team, I'm working in my team, and one of my team members did not show up to work today, if you are not using Run AI, his GPUs will simply sit under his namespace, again, idle. With Run AI, my teammates' GPUs can be allocated and provisioned dynamically to myself, so suddenly I can be more effective, more productive. I can have all the cluster to myself, assuming I was the only one who came to work. So we bring this dynamic solution, we start moving GPUs between the different users and teams and divisions based on the exact policies on the priorities of the users. And of course, there are many ways to tune the system. We support distributed training, we support bean packing and consolidation, we are aware of the topology of the hardware. There are many things that this resource management tool can do, where again, the end game is again to make sure all GPUs are utilized. A unique feature that I would like to maybe double click on is our ability to take GPUs and slice them. In most cases, when we're talking about interactive workloads or deployments, definitely you do not need to provision a full GPU. If you are provisioning a full GPU to a Jupyter notebook or to a model, you are wasting your resources. What we can do is we can take any GPU type, and this is important because we can do it on any GPU type, Ampere GPUs and legacy GPUs, we can slice them. We can run multiple containers on the same GPU. So several models can run on the same GPU. Number of slices are not limited. It's based on the model, the type of GPUs that you have. So you can slice it to 10, 20, 30 slices, really depends on what you do, what you're doing. And I would say the great differentiator is that the users can simply change the slices, the size of the slices from their dashboard, from their table. Again, we are creating a disconnection between the admin and the users. We want the users to focus on the models, to focus on their jobs. We abstract to them the hardware or the infrastructure fully. We don't want them to bother about what type of GPU, what is the networking, etc., etc. If a user needs 20 gig of memory, he should get a 20 gig of memory. It doesn't matter if it's 20 gig from a V100 or A100 or H100. He asks for 20 gig of memory, we make sure he will get 20 gig of memory. So again, any GPU type, number of slices is not limited, and users can change the slicing in runtime. No need to do any reset. Does not need to, again, cross the corridor to the admin to change something. All can be done directly from the user table. From a vast experience that we have, this is what we can bring. This is really what we can bring, or this is what customers can expect. So when we are starting with a customer, and after we finish the onboarding and the tuning of the platform, we can expect between 2 to 5x increase in the utilization, which immediately diverts to 10x more workloads that users can submit on the same cluster. I'm talking about even without adding a single GPU, right? 10 more workloads, 10x more workloads on the same cluster without changing anything, just by using Run AI. And again, we are talking about a huge increase in the ROI due to that. To manage all this, of course, we have a user interface. The user interface serves both the admin and the users. For the admin, it gives you full visibility into everything that is going on in the cluster. nodes, GPUs, how many are allocated, how many are being utilized. We know how to detect the actual type of jobs that are running. All the information is visible for the admin, and from this user interface, he can set his policies, set his how he wants to tune the cluster. We can see many clusters from the same user interface, so it's really a single pane of glass. If you are having, for example, an on-prem and a cloud, still you can manage it from a single UI, right? Here you can see an example of what was the quota, right? You can see that each user get a quota of 1, but essentially, for example, this user is using 10 GPUs, although his quota was 1. And this is, again, due to the over-quota mechanism that RunAI has for providing idle GPUs and pushing them to the users, assuming there are idle GPUs in the cluster. So it's a control plane for users. We support CLI as well. We collect, this is a multi-cluster view, but we will collect all the metrics, everything which is going on the cluster, either for tuning, for learning, and also for chargeback. We do work with customers that use our platform as GPU as a service. So they are actually, we are being the infrastructure for the GPU provisioning, and they charge per the GPU usage. So we collect all the metrics and everything which is going on. And again, this UI is not mandatory. We support CLI as well. 2 use cases, which again, I will not go into the details. I will just want to emphasize the numbers. One is the Bank of New York Mellon, and you can look at it at several ways. So this is the numbers that were given from the bank, right? 10 times more GPU were available, 20 times more workloads has been submitted. The utilization went up for 5 times more, and the system is fully automatic. No more manual things on your GPU clusters, right? No more Excel files, documents, or managing resources in a manual way. And you can see that when we're looking at the cycle from writing a model to deploying it, this is really the game-changing thing, right? You can see for the bank, and for the bank, you can understand it's a millions of dollars. In the first year of using RunAI, only 4 models reached the deployment stage, right? Finished the writing of the model, the debugging of the model, the training of the model, and deployed it. On the second year, 40 models has been reached the production stage, which is a 10-time increase in the models, and the numbers that the bank can make out of it is amazing. The last slide that I have is Adobe. If we are talking about BNY is an on-prem cluster. Adobe, we are managing, I think they have like 30,000 GPUs. We are managing their clusters in EKS, just showing you the capability of what happens when they are using RunAI. You can see that we have here several users which are running distributed training jobs, or I would say a single job across 1,000 GPUs in the cloud. So again, the diversity of the things that you can do with RunAI is amazing. It's really an end-to-end platform, and it doesn't matter if you are doing deployment only, training only, or interactive only. You can simply take it and you can simply tune it to whatever or how you want to build your cluster. This is what I had in mind, and again, from a bird's eye view about the RunAI platform and what it can bring to GPU or to AI/ML users.
Okay, thank you, Neil. There's a question. So there's some minute left, so you may answer lively. So what hardware platforms other than NVIDIA are supported? And secondly, if you have any business partner in Korea.
So currently, NVIDIA does not, again, assuming you're talking about something specific, today NVIDIA does not have this solution. NVIDIA does not have resource management solution. So not sure what it is compared to. Again, I think that the answer, the question was in Korean. So I don't know what type of tool exactly we are talking about. But today, NVIDIA does not have any resource management tools.
Neil, actually, the question is what hardware platform you are supported? Yeah.
The hardware is, again, doesn't matter. As long as you have GPUs and NVIDIA, NVIDIA GPUs and Kubernetes, it can be any type of hardware. We are first certified on the DGX, BasePod, and SuperPod. We are certified on these infrastructure, whether you are talking on NVIDIA. But again, we can work with Dell servers, HPE, Supermicro, Lenovo, Inspur. Our prerequisites is mostly GPUs and Kubernetes. We are agnostic to the hardware itself. We are agnostic to the networking. We are agnostic to the storage. We have customers that are using Weka, NetApp, DDN, VAST, any storage that they can use. We really need the GPUs and the Kubernetes.
And do you have a current business partner in Korea?
We do have several which are part of also the NVIDIA ecosystem, because we work very close with NVIDIA. So we do have some, yes.
Okay, thank you for the answer. 일단 답변을 드렸습니다. 혹시 추가적인 질문 있으시면은 동일하게 남겨주시면 되고요. 지금 다른 질문이 올라온 게 없기 때문에, 그러면은 마지막으로 사이버드의 설립자이시자 CTO이신 Dr. E.R. 바이스님의 발표가 있겠습니다. So, Dr. Weiss, the floor is yours.
Thank you. Let me share my screen. All right, and thank you for having me in this talk. Sounds very interesting so far. I'm coming from a completely different direction. First, I do a quick introduction of myself. Background mechanical engineering, plasma physics, and then a PhD in electronics engineering, to technology development. I came to found Cybord after I was working for 15 years for like a lifetime project with a large team of scientists and software engineers and physicists developing a completely new technology. And then when it was ready to deploy it in the field, after just a few months of deployment, we got some failures. And of course, everybody blamed the new technology. It was really new. But eventually, it came down to faulty capacitors that was introduced during manufacturing that caused this failure. This was a $1 billion project that was almost canceled because of a 1-cent capacitor. And when we went to the manufacturers and asked them, how come you don't check the components before you use them? They just told us there's no such thing as testing the components. Just buy them from a trusted source, and that's it. So the project was almost canceled. Eventually, it was successful, but was delayed by a year. So when it ended, then I founded Cybord to address specifically that. Now, what we are saying is most of the electronic components, most of the failures in the electronics industry are actually coming from the components, not the process. Why is that? It's because the process is so good. Technology today for manufacturing assembly is top of the line. Every aspect of the process is monitored. But the components, you just buy. There's no testing, there's no technology involved in checking the components. So you just buy them from your trusted source, which we invest a lot of effort to build, but that's it. There's no testing, technological testing of components. So it leaves most of the failures, about 80% of the failures in the electronic industry are caused by defective components, as you can see in these images. In fact, about 3% of all the assembled boards, at least, contain defective components that are responsible to these failure rates. And in addition, because all this industry is basically built on trust and information that delivered by the supply chain, all the traceability information is not accurate. There's 7.5% cases of mismatches between what you think you're using and what you're actually using as a component on your circuit boards. So because there's no technology to actually go into the components, the quality is not assured, and the traceability information or what you think you're using is not secured. Now, what we're saying is something very simple. If you could have looked at every electronic components just before you're placing them on the circuit board in the assembly process. Then you can just look at them and see what is written on top, so you can verify what it is. So this is the component you're supposed to use. You can look on the bottom side and see that everything is in good shape and quality. There's no defects, corrosion, or whatever. And only then place on the board. Now, of course, this is not practical to do it by hand, so we're using AI to do that. And it seems like an impossible task at first because there are hundreds of millions of types of components. So it's like impossible to build something that could correspond to this. But what we're actually doing is using the diversity of this large amount and deviations to our advantages, and we're building very efficient AI models for that. The AI models are built on big data, and we have already collected about 5 billion components for that. And this is how it works. Now, how are we doing this? As I told you, we have to look at components. We have to have somebody that's already taking pictures of the components for us, because we don't want to add any process to the manufacturing. So we're a software company, and we're connected to the pick and place machines like Fuji, ASM, Yamaha, and so on, which are taking up component, and then there's a picture taken from the bottom side to do alignment. And this is taken anyway without us. And we're taking those images so we see the components from the bottom side, every one of the components just before they are placed on the board. So this is what we get from, this is where we get the images from the bottom side of the component. Now from the top side, there's an AOI machine. AOI is automatic optical inspection machine that is looking at the top side of the board. Again, it is focused on the process. It doesn't care about the components themselves. We just want to see that they are placed correctly. So we are getting the images from the AOI machine, and we get the top marking of the components where we can understand what it means. And this is what's new about this section. We don't just read OCR. That's not interesting. We're understanding the meaning of what is written on every component, and then we can check if this is what we were supposed to use. So from the bottom side, we're looking at quality and authenticity. I will go into this soon. So we can check if the component is a counterfeit, if it's original, it is defective, corrosion, cracks, whatever, as you can see in the examples you can see here. And from the top side, we can see that we're using the right material and we have the right traceability information about every individual component. Now, so from the pick and place machine, where we have a partnership and working with both Fuji and ASM, we're now growing this. So every picture is drawn from the machine and we can analyze it. Actually, today we can analyze them on the fly. So if there's a problem with a component that we find that is problematic, our software using a GPU is fast enough to respond within 5 milliseconds time to the machine, so the machine can drop the component and not place it. This section is ready from our side. We are now working on the integration with the machine. So from the machine, from the solution point of view, it's going to be ready in a few months. But the analysis and the ability to block contaminated reels or defective boards is already available and is working for a few years now. Very, very good success. So this is the part about getting the images from the bottom side and looking for quality issues. A few examples. You can see a body defect. This is a resistor. Of course, a resistor is a very small component. Who cares, right? A resistor will cause, my project was almost failed because of a capacitor. So any component can fail your board. Doesn't matter. It doesn't have to be in a very expensive NVIDIA chip to fail the system. You can have a very small capacitor to fail it. In this case, the entire reel was contaminated with this defect, and we blocked the entire reel, and we saved all this hassle to the manufacturer. The other part of failures that you can see is like a statistical random failures. In this case, I'm showing, again, only passive components, but it's for all the components. So all the random failing components today, they're just part of the failures that you absorb. You solve your technological problem today with money, because you leave money for recalls, for warranty claims, and such so on. But you can solve the technological problem from the source, just making sure that you're using only good components. Now, the other part is, again, as I said, from the AOI machine, we're getting the images from the top side. And from the top side, we can make sure that the right material is being used. For example, in this case, the wrong part number was placed. So it's not that the traceability information is wrong, but the wrong material was used. So the product was not functioning properly. And we detected it early on, and we stopped it after the first or second boards were assembled. Otherwise, you would assemble the entire 10,000 board batch with the wrong material. So that's one aspect of it. The other aspect is having the correct traceability information. Here, in this case, the system automatically detected that the date code here is 223332. So it's year 23 with the week of production 32. So if you would have need to recall this product because there was something wrong with this specific one, in reality, the true date code as it was written on every component is different, was 2323. So it doesn't matter if it's older or younger, it doesn't matter, because if there's something wrong with this specific batch, then you would have recalled the wrong one. And the number of errors, as I told you before, about this kind of issues is 7.5% in top tier manufacturers. In some cases, we had as much as 50% errors in the documentation or understanding what material is being used. Now, this is a software, and this is a completely open API. So the idea is not to add any more process and work, and somebody needs to look at the system and see if the material is good or bad. The idea is that everything will be done inline and automatically. So if there's a fault detected, then the API will automatically signal the production machine to move this board aside. And it automatically flag the MES system about this and block automatically contaminated reels. So it's going to be completely automated. That's the idea, not to have another person trying to work it out, because will not work in this kind of industry. Another thing is that you can use, because you're looking at every individual component during the assembly, you can make sure that they all comply to the standard that is required by this industry, which is IPC 610 or IPC J001. Today, there's no verification because there's no technology that actually looks at the components. No, none of them. So everything is done to assess this only after a failure. Here, you can do a proactive method and detect all these issues before they're even occurring, before they are being placed on the board, and you can assure that you're complying to the IPC standard. So basically, this is the first method that is really using AI technology for the assessment itself. Again, every component, you know from which reel it came, you're looking at it from the bottom side. From the bottom side images, you can see if it's defective, there's corrosion, bent leads, cracks, whatever. And you can also see that if it's a counterfeit or not. Now, many people ask, how can you tell it's a counterfeit? Well, it's not that difficult because think about it. Even if it's a very small capacitor, let's say made by Murata, we have seen millions of them before. And we also seen millions of capacitors made by Samsung or Washington, whatever, any other company. So we can tell them apart using a very accurate AI model. Today, the accuracy is about 99.8 or 99.9% accuracy. So is the recall. So the accuracy is very good. What we are actually doing is not identifying the part number and therefore identifying the counterfeit. We are identifying the fingerprint of the machine that packaged the components. This is what we can get. And because of this is so efficient. Otherwise, it's going to be impossible to train so many models and so many variation of components. So that's the secret sauces. It's also, of course, patented. And this way we can scan many components and place them on the board. Now, after we have scanned them, we have in a database a lot of information about the components. We know which are the good manufacturer, which is the bad, what is the failure, what is the defect rate, what is the corrosion rate for every different manufacturer in every location that we are deployed, and we are already deployed in many locations. So based on that information, we can use it as data. So if you want to make procurement, for example, today you're just buying components based on who's the cheapest one and who's the most available one. But now you can use it based on reliability and quality information, which is much more powerful. This technology is now also being adopted where we're playing with very big players like NVIDIA, Intel, working also with other companies. We're deploying now in Flex Global, and we're studying further on. So the more data we have, the more lines we are connected with, the higher accuracy the algorithm will be. So the value proposition for the OEM is not just making sure that the quality is good in manufacturing, which is the CM responsibility or the contract manufacturing responsibility, but we are giving you information, the tools to have accurate traceability for every individual component. Every board that you have out there in the field, you don't have to ever do a batch recall because every one of them is in the database. So if there's a fault in one of the boards, you can see exactly how it looked like from the bottom side and from the top side during the assembly time, and use it to do failure analysis or smart recalling of this information. So for the OEM, it's not just assuring that the quality of production is good, but it's also assuring, it's like a warranty that your materials were using only good materials, and if there's a problem, you can always find exactly how it is without bringing back tens of thousands of units to do a recall. So it allows you to ensure the reliability, to validate the traceability information, to do forensic root cause analysis, and eventually to get analytics about the information and have make decision based on data that you have already collected and used, and not just based on suggestions. Thank you very much. If you have any questions, I'd be happy to answer, of course.
Thank you, Dr. Weiss. 네, 좀 혹시 질문하실 내용 있으시면은 올려주시면 되고요. 저희가 요즘에 인공지능이 워낙 좀 핫한 주제여서 오늘 뭐 이렇게 이스라엘에서 다양한 분야의 인공지능을 하고 있는 뭐 양자 컴퓨팅부터 또 이런 그 가상화 기술, 그 다음에 또 이런 제조 쪽에 사용되는 비전 기술 이런 업체들을 좀 같이 섭외를 해서 소개를 드렸습니다. 국내에서는 찾아보기 힘든 기술도 있을 거고요. 또 유사한 것도 있을 테지만 좀 차이점도 보실 수가 있으실 거라고 생각이 됩니다. 네, 질문이 더 없으시면은 오늘 이상으로 금요일 세미나를 마치도록 하겠습니다. 말씀드린 것처럼 오늘 발표 내용은 발표 내용 및 추가 자료, 그 다음에 연락처 정보 등은 등록하여 주신 메일로 제가 전달을 드리겠고, 별도 미팅 요청이나 추가로 궁금하신 점은 언제든지 연락을 주시면 됩니다. 네, 긴 시간 경청해 주셔서 감사합니다. To all the panelists, thank you for sharing your valuable time and then the very insightful pitch. Well, I hope this is gonna be some kind of a good lead inside of Korea to make a prosper collaboration between the country. So thank you so much, and I will make a summary mail within 2 days. So yeah, thank you
very much.
Thank you.
Thank you all. It was very interesting, enlightening. Thank you.
감사합니다. 네.
Good luck. All right.